All right, so the last part of this series on acetaminophen metabolism isn't actually going to go over like the real P450 mechanism, but it's going to show, I guess, a hypothetical reaction or hypothetical mechanism that doesn't exactly happen in acetaminophen, but it's applicable to a lot of the molecules. And with the problem sets and the tests, there's always like the phrase acetaminophen-like metabolism. So we're going to start right here on the left with acetaminophen. We're going to take P450. What the P450 is going to do is it's going to cleave the bond between the N and the H, and we're going to generate a radical. Okay. Hypothetically, let's say we wanted to hydroxylate this nitrogen. We would take our oxine atom. Okay, the oxine atom is electron deficient. We're going to attach it on there, and we're going to have OH. Okay. Now, when we have the nitrogen hydroxylation, what we can do is we can take this oxygen, we can push. When you keep pushing and you use the OH as a leaving group, that's your whole chemical step where you generate the aminoquinone, which is, again, susceptible to nucleophilic attack. The first step actually does happen, right? And this is a real intermediate, but everything that I put in blue doesn't actually happen, okay? It doesn't specifically happen in acetaminophen, but there are molecules that have very, very similar metabolism. Okay, so everything in blue is hypothetical. In going from this transition state or this molecule to the aminoquinone, there's some complicated mechanism that we didn't really discuss. Okay, but there are important concepts that we should discuss with regards to elimination from a para-electron donating group and whether or not it can happen with a para-electron withdrawing group. Okay, so we have our little conjugated system, and if you have an electron donating group that's para, okay, right here I just replaced the OH with an OSO3 because you can convert OH to a sulfate, but this would also apply if there's an OH right there. If you have an electron donating group, what can happen is this X molecule can push into the ring, okay, can push into the ring, and then what's going to end up happening is you will, in fact, generate an aminoquinone. Okay, you're going to generate this aminoquinone. Generally, the X is going to have some sort of positive charge, and then if it's like, let's say OH, you can deprotonate it to make it neutral. Okay, so if you have an electron donating group that's para to a nitrogen like this that's hydroxylated, what's going to happen is this form, it's not going to be very, very stable. Okay, it's not going to be stable. It's going to prefer to convert to the aminoquinone form. And then again, we have a Michael acceptor form, or we have the Michael acceptor functional group, which is susceptible to nucleophilic attack. Okay, with your synthesis problems, you could use this as a way to, I guess, attach GSH or some sort of other nucleophile. If it's on a conceptual question, you can say this is where the toxic effect comes from. Okay. Last thing that I want to mention about the electron donating groups, common ones you're going to see are OH and O with an alkyl group attached, such as OMe or OET. Okay. On the other hand, if you have a para-electron withdrawing group, okay, one of the reasons why this sulfate or this OH gets kicked out is because the group that's para at the bottom donates electrons and pushes everything out. Electron withdrawing groups, what those do is they don't push electrons in there. Okay, they just pull the electrons out. Okay, they pull the electrons out. Commonly, you're going to see this with like chlorine, bromine, or like NO2, something that withdraws electron density. So there's going to be no aminoquinone formed because you can't push electrons and kick this group out. Okay, in fact, if you have a para-electron withdrawing group, what that's going to do is it's going to help stabilize a hydroxylated nitrogen or a sulfated nitrogen, and you're just going to be free to excrete it. Okay, so the pathway that I just drew above, hypothetical. Okay, it's a hypothetical pathway for acetaminophen, but there's important concepts about hydroxylation of nitrogen. If you have something that's electron donating and it's para, you can kick it out and generate an aminoquinone, and then you're subject to immunotoxicity or nucleophilic attack by something. Okay, and that can be bad. If there's a para-electron withdrawing group, it's going to help stabilize, and then the OH, that the hydroxylated nitrogen or the sulfated nitrogen, can be stable, and when that's stable, it just gets excreted and you don't have this aminoquinone toxicity risk. Okay. This is like the basic little shelf or basic little framework for generating an aminoquinone and doing some immunotoxicity. What you have to start doing is look at the problems and start recognizing maybe it's not just one ring away, but there might be multiple rings away, and see how you can push the electrons to either generate a double bonded N, or if you can't generate a double bonded N. And that's going to be your way to figure out, is this going to be toxic or not toxic?